In this video, I'm going to show you some really cool things that you can do with the simple definition of acceleration. Let's start by writing down the definition. I'm going to label this definition as equation 1, and we want to keep track of the equations that we create during this video, during this lecture, so that we can reference them later. I'm just going to do this over here in the margin. This is equation 1. Okay, so the first thing that I want to do is I want to write this equation in a slightly different format that's related to the velocity time graph. So when we graph velocity versus time for an object, let's say that that object is accelerating. So maybe we've got something like this. We can write the equation of this line. So first of all, in this unit, the acceleration, aka the slope of this line, will be constant. So the slope of this line will be constant. This will always be a linear function. We can write the equation of this line. Right, the velocity at any point in time is the initial velocity plus the acceleration value times the time. This, by the way, is y equals mx plus b type thing. So this is actually our second useful way of thinking about acceleration, velocity, time. All right, but we can do so much more with this one equation. Now let's take a look a little deeper into what we can do with the velocity time graph calculations. Just to remind us, previously we saw velocity time graphs in the last unit where the velocity was constant. So just, recall this. If the velocity is constant, we can cut that off at any moment in time and say that the displacement is this area, right? So we would say here that the displacement is this height here, or whatever this constant velocity is, times this width here, which is however long that chunk of time is. This is old news. This is not a new piece of information. But the new thing is, what if we had this? The object is accelerating. Let's say it starts from rest and it accelerates up to some velocity over some amount of time. So we're going to chop this off here at this moment in time. Does it work to calculate this area? Sure. Same approach here, though. This is not a rectangle. The displacement, let's think about how we can write this. That's a triangle. It's 1/2 base times height. 1/2 base times height. So the initial velocity here is 0. The final velocity is some number. So it's the 1/2 times whatever the amount velocity changes, times however much time goes by, right? So what if the object doesn't start from rest? Well, let's look at that. This object started at an initial velocity of 0. This object is not. So I'm going to chop this one off at the same amount of time. The slope of this line is the same as this other line, but you'll notice that now there's actually two shapes going on here. I've got a rectangle and a triangle. Let's figure out how to calculate that. So without putting any numbers on this, let's call this the initial velocity, call this value here the final velocity, call this here some final point in time. Good so far. I've just labeled some points on the graph. So I've got two areas. I've got area A and area B. The total displacement is the area of A plus the area of B. So let's do that. Displacement A. It's the initial velocity times whatever that time interval is. Now the area of B. It's the height of this triangle, final velocity minus initial velocity times however wide this rectangle is, the amount of time. So we can put these together, combine them. Total displacement is the initial velocity times the time plus this area here. Okay, so now we're getting into some algebraic manipulation. There's only one time that you need to follow this. We're going to get to an equation that you can use. So stick with me for a touch longer. This equation has a lot of different values in it. And for it to be useful, you would need to know the initial velocity, how much the velocity changes by, how much time goes by, just to find the displacement. That's a lot of work. So I want to take us back to this original definition here, or better yet, this equation here. Let's substitute out this value. All right, so change in velocity. Change in velocity is the acceleration times the time interval. How the heck did I get that? That is the definition of acceleration just rearranged. Delta V is A times delta T. Cool. All right, we're back down here. Change in velocity is this quantity. So just making a substitution here. Delta V, replace it with this, and then bring down this value here. The thing in the square brackets is equivalent to this delta V value. So I just need to do, there's one little simplification we can do here. Delta T times delta T, any number times itself, is squared. This equation is a super useful quantity, a super useful way for calculating. So we're going to label this as equation 3. Now, like I said, you do not have to know exactly how I got to this equation, but you do need to be able to use it. Recall that all this went back to finding a displacement from adding up multiple, like more complex areas. That's it for this video. Go ahead and try a practice problem now.